Welcome everyone. I'm Dr. V. Sagaredi, and today's topic is SystemVerilog Testbench Architecture. And we are going to build it step by step and starting from the very foundation. So, what if I told you that 70% of entire chip design effort is spent not on designing but on verifying? So, and at the center of all that verifications sits one powerful structure, that SystemVerilog Testbench Architecture. So today we are going to build this architecture from scratch, block by block and slide by slide. So that by end of this video, you will understand exactly how every component fits together, and let's get started. If you see DUT, so design under test. At the foundation, okay, so DUT sits at the bottom alone for now, but everything we build from this point onwards exists for one single purpose, and to verify this block. So what exactly is the DUT? We have three key points here. The first one is DUT is synthesizable hardware written in RTL, register transfer level. This means it's a real, it's going to become a chip, and it must work properly, perfectly. And the second one, DUT works at the bit and signal level. So it doesn't understand transactions or objects. It only understands zeros, ones and clock edges and uncontrolled signals also. So the third one is DUT has input ports and output ports connected to the test bench. So that directly connected to the test bench. So whatever the test bench send it, and the DUT process and send back. So things, if the DUT has a block box, so we know that what goes in, and we know that what should come out. That the test bench is what proves that it actually does. And if you see in the next verification environment, now on the top of the DUT, so we add the first major test bench block, the verification environment, simply called N. So this environment is the top level container of your entire test bench. So it is the block that organize every single verification component. So like a generator, driver, monitor, scoreboard, all live inside this environment only. So it has the four important things we need to observe. So one is it acts as a top level test bench block, so meaning it's the master container. And the second one, it instantiates all the test bench components. When the simulation start, the environment is responsible for creating every object that will do the verification work. And the third one, it connects all the components internally using a mailbox or TLM ports, and we will see exactly what those are shortly. And the fourth one, and this is the crucial, the environment support reusability. So you can plug this same environment to the different tests or different projects and different configuration without rewriting anything. So the environment is like a verification factory. So it contains all the machines, connect them together and produce one output, and whether it is pass or fail. So coming to the next generator. Now let's place the first component inside our environment known as the generator. So generator is starting point of all verification activity. So its job is simple but critical. So it creates the stimulus that will eventually be applied to the DUT. So it has three responsibilities. So first one, it generates random stimulus. So input data are transactions. So they are not raw signals. They are high level transaction objects. So think of a transaction as a packet of information. For example, a write operation with a specific address and also a data. And the second one, so it applies the constraint to the keep generated data should be valid. You don't want the random garbage going into the DUT. So you want meaningful random data that represent the real world scenarios, and constraints let you control that. And the last one, it sends these transactions to the drivers through mailbox or TLM channel. So which we will see connected in the very next slide. So the generator is the brain that decide what to test, and everything downstream just execute these decisions. So coming to the driver, so next component is the driver here, and this is where the test bench starts tacking directly to the DUT. So driver sits just below the generator, and it has the four key responsibilities. So first one, it receives the transaction from the generator and typically through a mailbox. It picks up that high level transaction objects and get ready to execute it. and it converts that abstract transaction into a pin level signals. This is the critical translation step. The transaction say write some data to at a particular location. The driver knows exactly which signal to toggle in which order, in what order, and at what clock edge to make happens on the DUT interface. And the third one, it drives the DUT inputs through the interface. So the interface is the physical connection point between the test bench and the DUT, and we will connect it visually in the next slide. And the fourth one is it synchronizes with the reset and control signals. So making sure it never drives the DUT before reset is released, and always align with the clock. So now if you take, if the generator is the brain, the driver is the hands, and it physically applies the stimulus to the design. So if you see the mailbox, and those are the interface connections. So now look at this slide carefully. So because something important has been added here, so we can now see mailbox connection between the generator and driver, and the interface connection between the driver and the DUT. Let's talk about both. Okay, here if you see the mailbox shown as orange vertical arrow labeled mailbox, so it is a built-in SystemVerilog inter-process communication mechanism. So it works like a message queue. The generator puts a transaction in, the driver picks it up, and both run as a separate parallel process. So the generator keep producing the transaction while driver is still processing the previous one. So it is a non-blocking and efficient and clean. So the next interface I shown as a purple bidirectional arrow at the bottom. It is also a SystemVerilog construct that bundles all the signal between the test bench and the DUT into one single connection. So instead of passing 20 individual signals separately, you pass one interface handle. So the driver writes to each, and the monitor will read from each, and the DUT is connected to each. So here simply we can say mailbox connects the test bench component to each other, whereas the interface connects the test bench to the DUT. So here two channels, two different jobs here. And coming to the monitors, so we have a write monitor plus a read monitors. So now we introduce these monitors, and notice that in this architecture we have two monitors, write monitor and a read monitor. So that's intentionally. So here why? The first one, it observes a signal activity onto the DUT interface, and it watches every signal transaction like a transition. So every bus changes, every output the DUT produce. And the second one, it converts the signal level activity into transaction level data. Just like the driver translates the transaction down into signals, the monitor translates signal back up to the transactions. So this makes the data meaningful and easy to process. And the third one, like it sends a collected data due to scoreboard for checking. So now why two monitors we have? So there are three responsible is under this monitor, but we have two monitors, one the write monitor and the second one the read monitor. So why these two monitors? So the write monitor sits on the input side of the DUT. So it captures what data was written into the DUT and send it to the reference model inside the scoreboard. Whereas the read monitor sits on the output side of the DUT, it captured what the DUT produced and sends it to the both monitors are commonly sent to the comparison logic inside the scoreboards. So these monitors are commonly passive in nature actually. So they never drive any signals, they only watch and report. So like if we simply say that the write monitor is witness to the input, and whereas the read monitor is the witness to the output. Together they give a scoreboard everything it needs to judge. And coming to this scoreboard, so here in scoreboard we have reference model as well as the comparison logics. So it is the most intelligent component in the entire test bench, known as the scoreboard. Simply we can say, look at this slide. The scoreboard contains two internal blocks. One is the reference model and the comparison log. Let's understand each one. So the reference model, this is a software model of your DUT's expected behavior. It receives the same input transaction that we are sent to the DUT from the write monitor, and it independently calculates what the correct output should be. And it doesn't care about timing or signals. It simply says, given this input, the output, the correct output is this. It's your golden reference. And the next one is the comparison logics. So these blocks receive two inputs. So one is the expected output from the reference model and the actual output from the read monitor, what the DUT really produced. So it compares them, and if the match, it reports pass, and if do not match, it reports fail, and logs exactly what was expected versus what was received. So why this is so powerful? Because the entire checking process is fully automated. So no waveform analysis here, no manual checking. The scoreboard does it all for every single transaction automatically. So the reference model is the answer key. Simply if we analyze, okay, the comparison logic is the examiner and the DUT is the student being tested every single clock cycle. So now coming to this coverage model. So now sitting above the scoreboard and watching over the entire environment. So it has four key responsibilities. First, it ensures all the features scenarios are tested. For example, running 1,000 simulations means nothing if they all test the same thing. Our coverage tracks what has actually have been exercised. And the second one, it identifies untested conditions or signals. So if a particular corner case has never been hit, then coverage will tell you. So that's your signal to write more targeted test. And the third one, increase the confidence in the DUT's correctness. So high coverage means high confidence. So low coverage means there are still unknown risk in your design. And the last final one, provides a measurable verification goals. So in the real-time project, the team sets targets like 95% of functional coverage before sign-off. So coverage makes verification quantifiable, not just like a feeling. So without coverage, you are verifying blindly. So with coverage, you are verifying with a map and you know exactly where you have not been yet. So now coming to this test layer. Now if we zoom out and add a test layer which wraps around the entire environment, the test is the director of verification. It has a few responsibilities we can see. So first one is it configures the verification environment, like setting a parameter, enabling or disabling certain checks, and customizing the environment for a specific scenario. And the second one is like it controls simulation flow. So applying reset, starting the stimulus, and deciding when to stop the simulation. And the third one, to specify what type of input stimulus will be generated. Okay, random, direct, corner cases, or maybe like a stress test, the test decides. And the fourth one, it decides which scenario or data pattern to use. So a normal written test or back-to-back retest or error injection test. So each is a separate test file. And the fifth one, it enables or disable coverage or checking block as needed, giving you fine-grained control over what gets verified in each run. So the beauty of the test layer is just you write, like if you write 100 different tests, each one targeting a different scenarios. So without touching the environment. So driver, monitor, scoreboards. So the entire verification infrastructure stays the same, only the test scenario changes. So like simply we can say that test is the script, the environment is the stage, and the DUT is the actor. Change the script, the performance changes. So the stage stays exactly the same. So now if we see test bench top. So finally that complete picture, it is this is a complete picture of test bench architecture. So known as test bench top. So the test bench top is outermost module. So every point of entire simulation. This is the entry point of entire simulation. It is a module, not a class. It has six critical responsibilities. So first one is it initiates the DUT and interface, creating the hardware connection point of view. And second one is create the test and environment objects, bring the entire verification infrastructure into life, and connect the test bench component to the DUT through the interface, completing the signal path and generating clock and reset signals, the fundamental control signal that everything depends on it. And also start and control the simulation, triggering the initial sequence of the events, and end the simulation and display the results. After all the complete, giving you the final pass-fail results. So test bench top is the main function of your verification program. So everything gets created here and everything runs from here and everything reports back to here. So now we see complete data flow. Now it is a full picture. Now we see, so let's trace the complete data flow through the entire architecture one final time, right? So test bench top generate clock, resets and instantiate the DUTs and interface. So test configure the environment and trigger the scenarios. Generator creates constrained random transactions, clear, and transaction flow via mailbox to the driver, and driver convert the transaction into signals, and then DUT take this via interface. Okay, DUT process the inputs and produce the outputs. Clear. So write monitor capture the input transaction, send it to the reference model, and the read monitor capture the DUT outputs and send to the comparison logic, and comparison logic checks expected and actual. Then it say pass or fail. Coverage model tracks all the scenarios throughout the simulation. So every component playing its role and perfectly coordinated and fully automated. So to conclude, the SystemVerilog Testbench Architecture is not just a collection of the components. It is a precision engineered verification system where a DUT is what you verify. If we say the interface is how you connect, and mailbox is how components communicate. The generator and drivers create and apply stimulus. The monitors observes the and reports, and the scoreboard check the correctness automatically. Coverage model ensure the completeness. Then the test control the scenario, and the test bench top architects everything, right? Master this architecture, you are ready for UVM, industry projects, and a serious career in VLSI verification. So that's a wrap for today's session, everyone. And I genuinely hope this slide by slide breakdown give you a rock solid clarity on SystemVerilog Testbench Architecture. If this video helped you, please like, subscribe and share, and with someone on their verification journey, and hit the bell icon so you never miss and upload new videos. So your comments and questions are always welcome. Drop them below and I will personally respond. This is Dr. V. Sagar Reddy. So keep learning, keep building, and I will see you in the next video. Thank you.